Okay, so we're going to look at the definition of the dot product and some things we can do with it. So one way we can start by defining the dot product is by just multiplying the components of your vectors and then adding together these products. It turns out that this is also equivalent to a geometric way of thinking about the dot product, which is I could also take the magnitude of A times the magnitude of B times cosine of the angle between them, and this will give me the same number as if I did it this way. And it's not at all obvious why these are equivalent. In fact, we're going to show at the end of this video why this is true. But in the meantime, let's just actually try to calculate this dot product for a couple example vectors. So here in example 1, let's say this is A. I'm going over 1i up 1j, and then we can have this vector B, which is going over 2i. So let's calculate the dot product of this two different ways. One way I can start, let's do it algebraically first. So I have just going to take each of the components, so let's look at their I components, multiply those, and then add the product of their j components, which the j component of B is just 0. And so we can see in this case that I just get 2. But I could also try to do this with a geometric definition because I picked two vectors where it was pretty easy for me to see this angle. If you wanted to imagine this on an xy axis, this may help. And you can notice this vector A is going over 1 up 1, which means this angle is going to have to be 45 degrees or pi over 4. So I just happened to pick vectors where you could easily eyeball it. That won't usually be the case. In this case, we can do the magnitude of A times the magnitude of B times the cosine of the angle between them, cosine of pi over 4. Okay, and let's calculate each of these. So the magnitude of A, that's the length of this vector. That's going to be the square root of 1 squared plus 1 squared, so square root of 2. Magnitude of B is just going to be 2 because this is just a vector of length 2 in the I direction, and then cosine of pi over 4 is 2 over square root of 2, and so together I'm going to end up back at 2. And so this was just showing how either way, doing it algebraically or with using the angle between them, I get the same value for the dot product. And then let's look at, give us some room here, these vectors here, which are very common. They show up quite a bit. I'll show you here. Let's call this x, this is y, and so this vector 1, 0, we actually have a name for it. This is the vector I hat, and this vector 0, 1 is the vector j hat. And so let's do the dot product again, both ways with them. So let's do it algebraically first. I dotted with j, and you can see what's going to happen with these because I'm going to end up with 1 times 0 plus 0 times 1, so I'm going to get 0. And we could have seen that even faster by just looking at the angle between them and noticing that this angle is pi over 2 and cosine of pi over 2 is 0. So if I had done it the other way, I dotted with j, I would have ended up with their magnitudes. It doesn't even matter actually, but I'll just put them here. 1 times 1, and then cosine of the angle between them is 0, so I get back to 0. And this, in fact, is going to be very important because anytime, I'll even make it very clear, this is a right angle right here. Anytime you have two vectors that are perpendicular, another word we use for that is orthogonal. Their dot products will always be 0. And if a dot product is 0 between two vectors, it means that they're orthogonal. So this goes both ways. Okay, now let's combine these two definitions to help us figure out an angle between a vector that's hard to do just geometrically. So if I have this vector A and then this vector B, and I want the angle between them, this is not something I can just eyeball like I did above with the pi over 4 or the pi over 2. So instead, we're going to look at both versions of the definition. So let's do it algebraically first. Let's see. Okay, so let's do it this way first. So I'm going to do components. So 1 times 2 plus 3 times negative 1 plus, and then 0 times 2. So the dot product I am getting here is negative 1. But I know that this also has to equal the magnitude. So I'm going to put it on the next line. This also has to equal the magnitude of A times the magnitude of B times cosine of theta, because that's the other way we can define this. And so let's do that. Magnitude of A in this case is just going to be square root of 10, because I'm squaring the components, so I'm doing 1 squared plus 3 squared, which is giving me 10, and then I'm taking the square root. And then magnitude of B is going to be 2 squared plus negative 1 squared plus 2 squared, and then I take the square root of that, and I should get back to 3. And then times cosine theta, which is what I don't know. But now notice this equation I've got. I now have negative 1 is equal to 3 times the square root of 10 cosine theta. So I can solve for cosine theta. This means cosine theta is going to be negative 1 over 3 square root of 10. And then I can just take the inverse cosine, and this will get me the angle. So notice here, I'm going to have theta is inverse cosine of negative 1 over 3 square root of 10. And that means theta is approximately 1.676 radians. And so I want you to notice in general what we just did here. We said that we know we can calculate the dot product based on the definition, like this. And this means I can solve for cosine just by dividing through by the magnitudes here, and then I can get the inverse. So it's just taking the equation and showing us, oh, this is how they're related, and I'm going to calculate the numerator using the algebraic component by component definition. Okay, before we do some more applications with the dot product, I want to show you quickly why these two versions, the algebraic and the geometric, are equivalent using the law of cosines from high school. All right, here we're going to show we can start with this definition, the algebraic definition of the dot product. So just say, hey, here's the rule, here's how we're going to define the dot product. And then from this definition, using the law of cosines, we'll end up being able to prove this is also equivalent. So our goal is to show that this is also equivalent to the geometric version that involves the cosine of the angle. Okay, so we're trying to get to there, assuming we start with this. And there's a couple things that I want us to go over first. First is the law of cosines. So most people are probably not familiar with it or may not remember, but the version most people do remember is if theta is 90 degrees, because then this triangle that we've drawn here becomes our favorite right triangle, and we all know Pythagorean theorem, or we're used to it. So this is really the Pythagorean theorem piece. But law of cosines generalizes the Pythagorean theorem for when your angle is not just 90 degrees. So one other piece that I'd like us to notice is using this definition, I want you to notice what happens when you dot a vector. So this is just a side note. Using this definition of the dot product above, what happens when you dot a vector with itself? So I'm going to end up with a1 squared plus a2 squared plus a sub n squared. And I want us to realize how this is related to the magnitude of the vector. So notice the magnitude was the square root of this. And this means that the dot product is just going to be giving us the magnitude squared. And that's going to be something we use in this proof. So I want you to see that connection. I can either rewrite the magnitude squared, or I can write it as the dot product of a vector with itself. Okay, so what we're going to do first is transform this law of cosines, assuming we were using vectors instead of just triangles with lengths. Right here, this A, C, and B were just the lengths of the sides, but now we're just going to rewrite it, and I'm going to write a vector on this side and a vector here for B. And then I'm going to write this side as a vector. So I'd like you to take a moment, put it on pause, and tell me how you could write the vector here in black in terms of A and B based on what we've done in class. Okay, so if you said this vector should be B minus A, you're correct. And if you're trying to remember how we can check that, I would use what we know about vector addition. Remember, if I wanted to add this vector A with this black vector, B minus A, I should get B back, and that's exactly what I see here. Okay, so let's go ahead now and translate. We're literally just going to rewrite this law of cosines in terms of vector notation. So first thing is C squared. In this case, we're calling that B minus A, and I want the length of that side. So the length would be the magnitude of B minus A, and then I'm going to square that. And that has to equal the length of the A side, which would be magnitude of A squared, plus the length of the B side, magnitude of B squared, minus 2 length of the A, length of the B, cosine of the angle between them. Okay. So let's actually expand this out now using our handy dandy little trick that we noticed up here, that the magnitude squared is the same as the dot product of the vector inside with itself. So we're going to expand that out here, and that means that our left-hand side is going to be equivalent to just the dot product of B minus A with itself. And then the right-hand side would be the dot product of A with itself, plus the dot product of B with itself. And then I don't really have a succinct way to expand this, so let's just leave these here still in terms of magnitudes. Okay, now using the definition of the dot product that we assumed, this version up at the top, we can show that the dot product is distributive and commutative, which means I can basically do a FOIL equivalent with the dot product. So this is going to be the same as B dotted with B minus 2 times A dotted with B. So there I use the fact that the dot product is also commutative. And then I have plus A dotted with A. Okay, that's the left-hand side. The right-hand side stays as it is, but now you can see some nice cancellation that we're going to get. And this is getting us almost to where we were hoping to be. You'll see in a minute how we get there. So here I have this canceling with this canceling with this, and my negatives are going to cancel. And so notice I end up with, we can cancel those negative 2's. That would help. So then I'm going to get A dotted with B is equal to, where we wanted to end up, the magnitude of A times the magnitude of B cosine theta. So this is how you can start from the algebraic definition and then get to this other geometric definition using the law of cosines.